reflection of plane wavefront by concave mirror. For this, let's draw a concave mirror. This is the concave mirror. This one is the plane wavefront. So this is the plane wavefront. The plane wavefront is obtained when we will get a plane wavefront. So plane wavefront is obtained when the source is kept at an infinite distance. On plane wavefront means the parallel beam of light incidents on the concave mirror here. Okay. So parallel beam of light or incident like this. Like this. When the light is incident on the concave mirror, generally what happens? It undergoes reflection. After reflection, the reflected rays are focused at a point on the. After reflection, they get focused at a point. Let us call this point as focus, principal focus. Now we join locus of all the points which translates with the same phase. You will get the concave mirror, or you will get spherical wavefront of radius r by 2. You will get spherical wavefront of radius r by 2, because when light incidents on the concave mirror, it gets after reflection, the reflected rays gets focused at a point on principal axis. So you will get spherical wavefront. For plane wavefront, you will get spherical wavefront of radius r by 2. Here r is the radius of curvature of concave mirror. In the board examination, they will ask one more question. What type of wavefront is obtained when plane wavefront is incident on the concave mirror? That is, what type of wavefront is obtained when incident on the concave mirror means we will get spherical wavefront. The answer is spherical wavefront. Okay. So it is not necessary to draw all this. Just you will draw like this. When a plane, just to draw a plane wavefront like this. So this is the concave mirror reflecting surface. So for this plane wavefront, we will get spherical wavefront. We will get spherical wavefront of radius r by 2. Okay. The answer is very simple. We will get spherical wavefront and the plane wavefront is incident on the concave mirror of radius r by 2. Next, refraction of plane wavefront by convex lens. When a plane wavefront is incident on the convex lens, this is the convex lens. Okay. When plane wavefront is incident on the convex lens, we will get a spherical wavefront like this. We will get a spherical wavefront like this. And a plane wavefront is incident on the convex lens, we will get spherical wavefront, because when a plane wavefront is incident on the convex lens, the refracted ray are focused at a point on the principal axis. So the refracted rays are focused at a point on the principal axis. Therefore, we will get a spherical wavefront of radius f. We will get a spherical wavefront of radius f. That is the focal length. That is the radius for this spherical wavefront. When plane wavefront incident on the convex lens, we will get spherical wavefront of radius small f. That is the focal length. What type of wavefront is obtained? When plane wavefront is obtained, when plane wavefront is incident on the convex lens, we will get spherical wavefront. Okay. Next, the refraction of plane wavefront through prism. Okay. When a plane wavefront is incident on the prism like this. This is the plane wavefront. plane wavefront. Okay. So plane wavefront is incident on the prism. Again, you will get plane wavefront as the refracted wavefront. You will get plane wavefront as the refracted wavefront like this. But this plane wavefront is little twisted. When plane wavefront is incident on the prism, you will get again a plane wavefront. But this plane wavefront is little twisted because here the light travels from rarer to denser medium. In the denser medium, its speed decreases. Here the denser medium is less, so it moves faster. Here, as we go away, here the denser medium quantity increases, so its speed here decreases. So it travels little less. Like this, it travels little less. So you will get again the plane wavefront, but it is tilted. So it will get twisted. Okay. So what type of wavefront is obtained? Well, plane wavefront is incident on the concave mirror. So you will get spherical wavefront of radius r/2. Then what type of wavefront is obtained when plane wavefront is incident on the convex lens? So you will get spherical wavefront of radius f. What type of wavefront is obtained when plane wavefront is incident? When plane wavefront is incident on the prism, you will get again plane wavefront. This is important from the point of examination. We shall discuss about Doppler's effect. Whenever there is a relative motion between the source and observer, the frequency received by the observer is different from that of the actual frequency. For example, this is the source of light and this is the observer. Whenever there is a relative motion between the source and observer, the frequency received by the observer is different from the actual frequency of the light, and this effect is known as Doppler effect. The different frequency is known as apparent frequency. Like the changing frequency is known as apparent frequency. Apparent frequency is the changing frequency of the light. Apparent changing frequency of the light when the source and observer are in relative motion. And what is apparent frequency? When the source and observer are in relative motion, the changing frequency is known as apparent frequency. That is changing frequency of the light when there is a relative motion between the source and observer. Okay, Doppler shift. The changing frequency of the light when the source and observer are in relative motion is known as Doppler shift. The changing frequency of the light when source and observer are in relative motion is known as Doppler shift. So this Doppler shift is given by delta mu by mu is equal to plus or minus v radial by c. This change in frequency is given by delta mu by mu is equal to plus or minus v radial by c. Here delta mu is the change in frequency, mu is the original frequency, and v radial is the radial velocity, and c is the velocity of light in vacuum. Okay, here v radial is positive, radial velocity is positive when source is moved away from the observer. Source is moves away from the observer. Away from the observer. Okay. And v radial is negative. V radial is negative when source is moving towards the observer. The source is moving towards the observer. V radial is positive when the source is moves away from the observer. V radial is negative when the source is moves towards the observer. Next, blue shift. When source is moves towards the observer, when source is moves towards the observer, what happens? When the source moves towards the observer, the apparent change in frequency will change. That means here, when the source moves towards the observer, the apparent frequency goes on decreases. The apparent frequency or wavelength goes on decreases. As a result of this, the spectrum of radiation shifted towards the blue region. Spectrum of radiation shifted towards the blue region. Therefore, it is known as blue shift. Okay, when the source moves towards the observer, there is an apparent decrease in wavelength or frequency, and as a result of this, the spectrum shifted towards the blue region, and it is known as blue shift. Similarly, red shift. Red shift is obtained when the source is moved away from the observer. This is source and this is the observer. When the source is moved away from the observer, there is an apparent increase in the wavelength. There is an apparent increase in wavelength. There is an apparent increase in wavelength. So, therefore, the spectrum of the light shifted towards the red region. The spectrum of light shifted towards the red region. Therefore, it is known as red shift. When the source moves towards the observer, there is an apparent decrease in wavelength. Therefore, the spectrum of the light shifted towards the blue region. Then it is known as blue shift. When the source is moved away from the observer, there is an apparent increase in the wavelength of the light. Therefore, the spectrum of the light shifted towards the red region, and it is known as red shift. Next, interference of light. Interference of light is nothing but modification of distribution of light energy. Interference is modification in the distribution of light energy. Distribution of light energy. When modification in the distribution of light energy, when two or more waves superpose on each other. When two or more waves are superposed on each other. This is known as interference. So, interference is nothing but modification of light energy. When will the light energy is modified? When two or more waves are superposed on each other. Modification means it may increase or decrease in the frequency or wavelength. Increase or decrease in the frequency or wavelength of the light. So, it is a modification in the distribution of light energy when two or more waves are superposed on each other. Before going to start the interference, we shall know some basic concept about superposition. I think it is already studied in first PUC in the chapter waves. So let's recall it. That is superposition. So principle of superposition states that when two or more waves are superposed on each other, when two or more waves are superposed on each other, then the resultant wave or the amplitude of the resultant wave may increase or decrease. The principle of superposition states that when two or more waves are superposed on each other, then the amplitude of the resultant wave or wavelength of the resultant wave may increase or decrease. So, principle of superposition states that when two or more waves, light waves, when two or more light waves superpose on each other, then the resultant, then the amplitude, frequency of the resultant will gets changed. Okay, that means it will increase or decrease. Or according to principle of superposition, the resultant displacement is equal to the sum of individual displacement. According to the principle of superposition, the resultant displacement is the sum of individual displacement, or it is a vector sum of individual displacement. Let us consider a wave displaced with an equation y1 is equal to a sine of omega t. The a is the amplitude, omega is the angular frequency, and t is the time period. The first period, the resultant the displacement of the first period is given by y1 is equal to a sine of omega 2. And let us consider one more wave, that is y2 is equal to a sine of omega t. Then the resultant of these two waves is given by y is equal to y1 plus or minus y2. So y is equal to y1 is a sine omega t plus or minus a sine omega t. This is the resultant displacement. So resultant displacement is actually vector sum of the individual displacement. Okay. When two sources are said to be coherent sources, if they emit light of same frequency, same amplitude and constant phase difference. The two or more sources are said to be coherent sources. If they emit light of same amplitude, same frequency and constant phase difference. Best example for coherent source is laser light. Example for coherent source is laser light. Okay. Thus coherent source is obtained by the single parent. Usually best coherent source is obtained by the single parent source. So if we kept a single parent source in between, in front of two small slits, like this. Therefore, this point source emits spherical wavefront like this. When this wavefront pass through these two slits S1 and S2, then we will get light of same amplitude, same frequency. These are the coherent sources. So coherent sources are obtained by single parent that pass through the two slits. Okay.